embarrassing. No. That bit took way longer to prepare and cost about 10 times as much as we were expecting. Welcome to Bad Astra. Hello again, astronauts. I noticed there are a lot more of you after our last video. Welcome to our wacky science channel, where we talk about space, physics, and combat science misinformation with more costume changes than math. I'm Astra. I have a BA in physics, an MS in mechanical engineering, and a habit of obsessively researching commenter questions. Eris, a chaotic witch and our writer, is responsible for a lot of our more high concept videos and has started appearing more often on screen. My wife, Nova, is the smart one and is finishing up her PhD in astrophysics. She's not only the science consultant on our physics videos, including this one, but designed our logo and is responsible for my makeup look today. Can you tell she's been watching Glow Up? Thank you all so much for watching our wacky science videos, and we'd really appreciate it if you like, subscribe, and leave a comment down below. I read them all, and I try to respond to most of them. If you really love our videos and want to support us paying for increasingly elaborate costumes, props, locations, and filming equipment, we have a Patreon where you can sign up to get early access to our videos, behind-the-scenes updates, blooper reels, and other fun perks. Ooh, also, we have stickers now. Every one of our patrons, as of Thanksgiving, will get a Bad Astra sticker mailed to them. They're great for sticking on phone cases, water bottles, laptops. They're stickers. You get it. Okay, back on topic. Our last couple videos were about calculus and science misinformation, and we've gotten several requests to update our last JWST video now that the telescope has launched and sent back data. So today, we're going to space, specifically to L2, to check in on all of the amazing views JWST has been posting on Instagram. I'm only going to use the acronym because this space telescope's namesake was complicit in a lot of homophobic stuff. And here at Bad Astra, we're queer scientists who don't want to get fired from NASA. Yay! So, are things going okay? So far, completely. JWST is performing even better than expected. Like Hubble, we can expect this telescope to define a generation of astronomy and of cool laptop wallpapers. The JWST is currently orbiting around L2, or the second Lagrange point in the Sun-Earth system. Lagrange points are produced by the balance of two or more opposing forces. In this case, the gravity wells of the Sun and the Earth. These points are useful because they are locations in space where gravitational forces and the orbital motion of a small body, like a probe or telescope, balance each other out. An object chilling out at a Lagrange point will not have to spend nearly as much fuel to maintain its orbit, and can just chill out and let itself be kept hovering in place by physics. All of these Lagrange points orbit the Sun at the same rate as the Earth, so they're not really points in space so much as relative points between the Sun and the Earth. L1 is between the Earth and the Sun, which is great for the Solar and Heliospheric Observatory satellite, SOHO, but wouldn't be great for looking into deep space, sandwiched between the Earth and a giant light source, the Sun. L2 is 1.5 million kilometers directly behind the Earth. It's 4 times further away from the Earth than the Moon. L3 is hidden behind the Sun, which would make it difficult to get any information back from it. For all we know, there could be a hidden planet behind the Sun.
No.
But probably not. Like, almost definitely not. There's no hidden planet. All three of these Lagrange points are unstable, meaning spacecraft have to make course adjustments regularly to remain in these orbits. For example, JWST makes a series of small station-keeping maneuvers over the course of each 21-day period, keeping it in place. But because of its position around L2, these maneuvers can be much smaller and require much less energy than maintaining a traditional orbit around the Earth would. L4 and L5 are the two stable Lagrange points, leading and trailing the Earth's orbit. So objects there would not need any course corrections to maintain their position. That means if you got a probe or ship hovering in orbit at one of those points, it could remain there without using fuel, theoretically forever. So what's currently there? Trojans. That's what we call the high dust concentrations and an asteroid at L4 confirmed in 2010 that tend to accumulate at Lagrange points. Space junk just tends to collect at stable Lagrange points because it takes more energy to leave them than remain. Lagrange points are great places to sit back, relax, get carried along by physics, and watch the stars, which is exactly what JWST is doing. So, what has it seen so far? Let's start with the first released images taken by JWST. This one is a star-forming region called NGC 3324 in the Carina Nebula, captured in infrared. It's really pretty and has way more detail than Hubble's image of the same thing, giving us a little taste of how much more powerful this telescope is. And here we have Stephan's Quintet, a visual grouping of 5 galaxies, which you might recognize if your family also watches It's a Wonderful Life every single year on Christmas Eve. It's amazing how much telescopes have improved in under a century. This one is the Southern Ring Nebula, which is a planetary nebula 2,500 light years away. Planetary nebula don't have anything to do with planets. They are the remnants of dead stars. JWST also found water in the atmosphere of a hot Jupiter, or a gas giant close to its star, using spectroscopy, or element fingerprints. While we probably won't find Vulcans or Andorians on a hot Jupiter, this ability to find extrasolar water is huge for the search for extraterrestrial life. But the final of these first images is the one I'm most excited about. SMACS 0723, or Even Deeper Field. This image, which covers a patch of sky around the size of a grain of sand held at about arm's length, contains thousands of galaxies, including the faintest objects ever observed in the infrared. We can also see a clear gravitational lensing effect, where a distant galaxy cluster bends the light from even more distant galaxies, distorting and multiplying them in a circle around itself. General relativity is so cool. One goal of JWST is to see the first instances of star formation ever, or population 3. The sun is population 1, or a third generation star. Yes, the numbers count backwards, it's astronomy, I don't make the rules. The early images from JWST show that we're getting really close to being able to see these Pop 3 or first ever stars. Light from the most distant galaxy in this image has been traveling for 13.1 billion years, almost the entire age of the universe. Learning more about these super old galaxies and the early universe will dramatically improve our understanding of how the universe formed. Currently, we're relying on theory and computer simulations. Getting observational evidence to confirm or refute what we think we know will be fantastic. Light from galaxies in another JWST image may be as old as just 300 million years after the Big Bang. One of those galaxies seems to have already built up a spiral disk about 1 billion times the mass of the sun, which is very unexpected. That's shockingly mature for a galaxy from that early in the universe's life. Many of the super old galaxies in this image also have mature disks, rather than being disorganized blobs or mostly made of dark matter, as astronomers originally expected. So our understanding of galaxy formation in the early universe has already been tentatively contradicted by JWST images, which is super cool. Now, I have to have a big asterisk on all of this since the super old galaxies don't have confirmed ages yet for reasons we'll discuss in a minute. Remember, this data is super new, and good science takes time. Some galaxy ages have been confirmed using spectroscopy, by taking a spectrum and finding the redshift of the hydrogen and oxygen lines. Element fingerprinting, which is very reliable for determining how far away something is and its age. In astronomy, an object's distance in light years and its age are the same, since that's how long it took for the light to get to us. But why is the shifting important? Cosmological redshift, caused by the expansion of the universe, is the effect of photons' wavelengths getting stretched out as they travel across vast distances. This stretching makes the wavelengths longer, or more red. We can tell how far they've traveled by how stretched out, or redshifted, they got along the way. We know hydrogen's chemical fingerprint very well. It's the most common element in the universe. And even when all the light gets redshifted, it all gets stretched by the same percentages. So if we know the distance ratios between the hydrogen emission lines, we can find where they've moved to. Once we've identified how much they've been stretched, we know how much all the light has been stretched, and therefore how long the light was being stretched and how far it must have traveled in that time. Another method of determining galactic age, which the media may not have been critical enough of, is photometric redshift. Nova calls this method sketchy and points out that the galaxy formation contradictions I mentioned earlier are tentative at best. Photometric redshift is a quick and dirty redshift estimate. Taking a full spectrum to find the emission lines of something far away takes a lot of time, since you need to collect a lot more light when you're splitting it up. And observing time on JWST is not easy to come by. So instead, you put the limited light you do have through some filters and look for the Lyman break, a sudden place in your spectrum where above a certain frequency or below a certain wavelength, the light suddenly becomes a lot dimmer because it's energetic enough to ionize hydrogen and be absorbed. These photons don't need to be that perfect fit of bumping up an electron to a higher energy level, since they can just rip the electron clean off. Since those higher energy photons just past the Lyman limit are more likely to get absorbed, far fewer of them get to us. Since we know where that sudden break in the spectrum should be, if we can find that large single break in the spectrum, we can see how far it's moved and calculate the redshift from a single point without needing to find a bunch of different lines the right ratio apart. This is sketchy not just because one line is less reliable than several, but also because you're not looking at this pretty full spectrum. You're just sampling 3 to 5 points, looking for 1 to 2 points on the high and low sides each to guess where the Lyman break is. What if one of your data points hits an emission line? What if your galaxy just happens to have a short, weird feature in its spectrum? These spectra are not perfectly linear with a single sudden dip, and sampling just a few points is not a replacement for gathering the full spectrum. Further study is always needed when using photometric redshift. Photometric redshift as a method is great for identifying candidates for super old galaxies, but not for identifying age on its own. But it's a great tool to have, and I'm excited to see what further study reveals. Tangent about how great JWST is for a second. One of its huge advantages is that it can collect full spectra in a much shorter time than Hubble, because it's huge and collects a buttload of light. So full spectroscopic redshift measurements, the much more reliable method, are a lot easier. We just need to wait a little bit for the astronomers to do the science. I hate waiting. Before we move on from this image, the foreground galaxy cluster is also super interesting on its own. The uneven light from lone stars between the galaxies in the cluster is evidence that this cluster is likely the result of a cosmic collision between two smaller clusters, which flung these stars out of their host galaxies. Given the uneven distribution of these lonely stars, astronomers think that this collision is ongoing and the dust hasn't yet settled. Our next post from the JWST is the Cartwheel Galaxy, 500 million light years away. Galaxies with rings are really rare. This one has 2 rings. Astronomers think that it used to be a large spiral like the Milky Way until a smaller galaxy smashed through it. JWST project scientist Klaus Pontoppidan compares the collision to dropping a pebble in a bathtub. First, you get this ring. Then it hits the walls of your bathtub and reflects back, and you get a more complicated structure. Let's compare this image to the one taken by Hubble. Not only do we see way more detail, but the new infrared image shows bright spokes, which are sites of intense star formation. These star formation regions were likely triggered by the aftermath of a galactic collision. But why are there spokes? Astronomers aren't sure, which is really cool. More recently, JWST found CO2 on a hot Jupiter exoplanet. Carbon dioxide, or CO2, is a key chemical species that is found in a wide range of planetary atmospheres. So finding evidence for this molecule is not in itself exciting. WASP-39b is a hot Jupiter, but even less dense. This gas giant is wider than Jupiter, but only as massive as Saturn. It orbits super close to its star. A year is only 4 Earth days. This exoplanet is a terrible place to search for evidence of extraterrestrial life, but the low density atmosphere and frequent passes in front of its star make this planet super easy to observe. A perfect planet to test JWST's instruments and capabilities. And JWST just passed its first training course. I'm really excited for what it'll find when we look at terrestrial planets in Goldilocks zones. Speaking of looking at exoplanets, JWST did just that and captured the first ever direct image of an exoplanet. That Jupiter image was super cool and detailed, and we all loved seeing Neptune's rings with more clarity than ever. But this is next level incredible. Usually, we can't directly see planets orbiting other stars because they're tiny and very far away. Instead, we detect exoplanets by observing the light from their star dimming slightly when they pass in front or transit, and the star's slight wobble as the planet's gravity pulls it ever so slightly closer and further away. The relative dimming of the light tells you how big around the planet is, and the wobble tells you how massive it is. If you have both, you can calculate the planet's density and know whether it's gaseous or terrestrial. During the transit, the starlight passes through the planet's atmosphere, and you can see what wavelengths of light the planet's atmosphere absorbs, which tells you what chemicals are in the atmosphere. JWST directly imaged an exoplanet, It slapped a coronagraph filter to block the light from the host star and collected reflected starlight from the planet. It's a gas giant, and we can see it. Not an artist's rendering, but actual photographs at different wavelengths. This is a huge step forward in the search for extraterrestrial life. Do I need to explain the science implications of that, or can we just sit around and be giddy for a moment? Most recently, JWST also captured images of the DART impact, which isn't exciting for the telescope, but is a super cool test of our planetary defense system, so I'm going to talk about it anyway. DART, NASA's double asteroid redirection test, was an experiment in which we intentionally smashed a spacecraft into an asteroid and, like any good YouTuber, sent a companion along to film the whole thing, and filmed the collision and aftermath from a bunch of angles. Dimorphos is a tiny asteroid which orbits another asteroid, no threat to us at all, and we just smashed into it with a vending machine-sized battering ram traveling at 22,000 kilometers per hour. Nancy Chabot, DART mission team leader, describes it as running a golf cart into a Great Pyramid. Okay, I want Nancy Chabot to describe everything from now on. But why did we do that? Besides the truly epic space explosion. Astronomers have theorized that we could potentially change an asteroid's course by hitting it with a fast-moving object. It's complex physics, best demonstrated in the following clip. Let's break that down. You'll notice that Brutus the Buckeye changes trajectory when hit by the fast-moving bubble boy. This same principle of moving a big object with a fast collision can be applied purposefully, as demonstrated by the Special Task Force rescue in this next clip.
Mission log. Have reached Zerg's command deck, but no sign of him or his wooden captive.
Please! No! That's Woody! What are we gonna do, Buzz?
Use your head.
But I don't want to use my head!
You'll notice that the targeted impact of Rex's head on the large vent door moved it. Anyways, DART's goal was to do the same thing in space, moving an asteroid by hitting it really hard. Dimorphos used to orbit a much larger asteroid, Didymos, every 11 hours and 55 minutes. But NASA thought that by absolutely bodying it with a probe, they could get that down to 11 hours, 45 minutes. They designed DART to go fully autonomous and target lock on Didymos with its camera, like smart missiles out of Star Wars, able to distinguish between the two asteroids and knowing not to charge the wrong one. There was a backup plan to swing back around if it missed, but this battering ram found its target and sent images back until its last moment of kamikaze glory. But why would NASA want to change a random asteroid's trajectory? Well, if you've seen Don't Look Up, or The Expanse, or any of several dozen disaster movies, or learned about what happened to the dinosaurs, you might know the dangers of a large asteroid crashing into the Earth. Now, Dimorphos was and is not a threat. This was a test. NASA successfully ran the world's first test of the kinetic impact mitigation technique, using a spacecraft as a battering ram to deflect an asteroid and modifying the asteroid's orbit. This is a proof of concept for potentially defending Earth against incoming asteroids. Amazing what happens when you fund scientists, believe them when they demonstrate potential threats, and give them the tools to develop solutions. Good thing we're doing that with all of our other global catastrophes. JWST and Hubble captured simultaneous images of the crash, which is the first time the two have ever worked together like this. Since Hubble captures optical light and JWST captures infrared, astronomers can learn a lot more when they work together than from either working alone. Speaking of telescope teamwork, let's check out those first JWST images, now with added observations from the Chandra X-ray telescope. Teamwork makes the dream work. And my dream is to have even more public domain images to use in these videos. The JWST can look at the atmospheres of exoplanets. It can see galaxies from the early universe. It can capture more details and see through dust like never before. The most exciting part of all of these findings is that none of them pushed JWST. These have all been short, easy, testing the system measurements, which means the best is yet to come. This telescope is not just working, but exceeding all expectations. JWST is a revolutionary step in astronomy's quest to answer two of humanity's biggest mysteries. Where did we come from? And are we alone? This telescope will change our understanding of the universe. And I am so excited to learn what we were wrong about and what we didn't even think to consider. Astra out.
Ad Astra, to the stars, to the stars.